This is part 3 of the chemical changes topic in GCSE AQA chemistry. It's a dual and triple award topic. In this particular video, we're going to take a look at reaction profile diagrams, how we can draw them, how we can recognize them, and how we can use the information to determine whether a reaction is exo or endothermic. So we have a question down here at the bottom. I'm going to recommend that you pause and have a go at activities as you go through. But if I were to turn on a gas tap, release some methane into the lab, what observations would we make? And in very simple terms, you would get the smell of the methane diffusing through the room, but you wouldn't actually have any evidence of any chemical change. There will be no observable chemical reaction. But we know that methane burns. So what would happen if your teacher ignited the methane? If they used a match or another means, a lighter, to actually ignite it, what would you observe at that point? And again, fairly straightforward, fairly simple. You'd get some large orange flames coming from there. They'll be familiar to you from the Bunsen burner, which is fueled by methane. There would be heat and light energy released to the surroundings. So we have a situation where the methane does not react with oxygen unless we provide that energy initially. And that's what activation energy is, the minimum energy needed for colliding particles to react. Now, we'll talk more about colliding particles in the rates of reaction topic. But as a simple analogy, we can think about this as being like a hurdle race, 110 meter hurdles. And as you're running, you are trying to get from one end of the track to the other. But you have the hurdles in the way, and you've got to get over those hurdles. You've got to jump over them. So you're going to put extra energy in to get to the other side of that hurdle. Now, the reason I'm using that analogy is because you can potentially see how that fits with the reaction profile that we see here. I've got my reactants, which have got a certain amount of energy, and I've got my products, which in this particular situation have less energy. But before I can get from reactants to products, I need to provide some energy to overcome the activation energy. So I've got activation energy, which is how much it goes up by to the top of our hump, and the overall energy change is the difference between what the reactants had and what the products have. Now, let's have a think about whether this is an exothermic or an endothermic reaction. And when you've had a think about it, press play on the video and listen to the answer. Well, let's put some information on. The overall change we can see here is that products have less energy, as we've already said. So the products having less energy than the reactants. Well, that means that that energy must have gone somewhere. It's gone to the surroundings. And if you think back to the previous video where we were introducing the concept of exothermic and endothermic reactions, when heat is released to the surroundings, the temperature of those surroundings goes up. So we measure an increase in temperature with exothermic reactions. This energy has been released. That's what will be measured as heat energy. So we are looking at an exothermic reaction because that heat energy has been released to the surroundings and the temperature will therefore go up. Now, I'm going to ask you to have a go, sketch out what you think the reaction profile would look like for an endothermic reaction. Remember, this is exothermic. Now let's try endothermic. And the axes stay the same. We've got energy on the y-axis. We have reaction progress or progress of reaction on the x-axis. And my reactants have a certain amount of energy. Now remember, in an exothermic reaction, energy was lost or released, so the product had less energy. But in an endothermic reaction, heat energy is taken in from the surroundings. That means the products have more energy. So that's the big change that we're going to recognise between the two that we're talking about. But I'm still going to need to put energy in. There's still going to be an activation energy. So I'm going to have activation energy going from reactants up to the top of my hump, the overall energy change is the difference from reactants going to product. Now, this will be a positive value this time, so the energy change is positive. In the exothermic reaction, it was negative, and we'll talk a little bit more about that in this and the next video. So, this is helping us to understand a calculation that's going to come up in the next video. We have a very simplified view of what's happening within a chemical reaction when we do these calculations. What we're essentially considering is that the reactants are taken apart to become individual atoms and then put back together, rearranged as the products. So there's two questions at the bottom here. Have a go at them. Well, the bit that relates to bond breaking is an endothermic process. Think about it. If you break something, if you snap a pencil, you have to put energy in. If you break a bond, you have to put energy in. We know that endothermic is taking energy from the surroundings, so the endothermic process, breaking the bonds, takes us to this theoretical position where all of the atoms have been broken apart. And then we have the bonds forming. So bond making is exothermic. It's the reverse. If it uses energy to break a bond, it releases energy to make a bond. Again, we will talk about that in calculation terms in the next video. The overall reaction here, it wasn't asked for, but it is exothermic because we have lost energy overall. More energy, and just looking at the reasons for that, it's exothermic because more energy has been released when the new bonds are formed than was needed to break the bonds in the reactants. So that takes us through the theory of reaction profile diagrams. As I say, in the next video, we're going to take a look at some calculations that relate to this as well. That's the end of this video. Thank you for listening, and goodbye.